All right. The last topic I'm going to discuss in today's lecture is going to serve as a little bit of a transition to the next lecture. So for the next lecture, we'll talk a lot more about attention, but I just want to introduce the notion of attention for seek-to-seek models. Okay, so there's a problem with sequence-to-sequence models which kind of limits the maximum length of a sequence that you can handle, which is what we can refer to as the bottleneck problem. Basically, all the information about the source sequence has to be contained in the activations at the beginning of decoding. The decoder doesn't know anything about the source sequence except what the encoder puts into the first hidden state. Nothing else is known to the decoder. And that can be a big problem when the input sequence is very long. So this forms a kind of bottleneck. Basically, the encoder needs to be really, really careful in putting just the right information into that first hidden state for the decoder, so the decoder will decode the right thing. So maybe we can relax this a little bit if we somehow allow the decoder to peek into the input sequence a little bit more while it's decoding. Like maybe this would work a lot better if essentially the encoder just put a general summary of what's going on into the hidden state, and the decoder could still reference back to the input sequence to pull out individual words. Obviously, this doesn't really matter when your input is of length 3, but imagine your input is an entire paragraph, right? And maybe that paragraph contains some facts about a historical event that happened in a particular year, and the encoder encodes the general gist of the paragraph, something about its structure, but it doesn't want to store the particular year when that event happened, so when the decoder gets to that point, it can just reference back into the input sequence and just pull out that token. So maybe while we're decoding, we want to somehow have a little shortcut that says, well, when you get to the subject of the sentence, if you forgot what the subject actually was, you can look back at the subject in the encoded sentence and kind of pull it in to the appropriate time step and include it in your input. How can we do this? If we could do this, we would greatly reduce the importance of that bottleneck. It would be much less critical for the encoder to be really perfect in stuffing everything into the bottleneck, and it would be much easier to deal with very long sequences where that's very hard to do. So how can we do this? How can we peek at the input while decoding? So here's the basic idea, and I'm going to outline the idea. It'll seem a little bit arbitrary, but as I describe it more and more, hopefully it'll be clear why it's designed the way it is. While encoding, we're going to have each step of the encoder RNN produce a little piece of information that describes what is present at that time step. That piece of information will not be semantically meaningful to us. It'll just be like a little vector of activations. It doesn't mean anything in isolation, but it'll be very useful later. So we call this a key. Intuitively, it represents what type of information is present at this step. But we're not going to specify the key manually. It's actually going to be learned as part of the learning process. So the mapping from the input hidden state to this key is some function, some learned function, like maybe a linear layer in ArrayLoop. In practice, oftentimes just a linear layer, basically a linear transformation is often enough. And then at every step when we're decoding, we're going to output a little vector of the same length that we call a query. So the query vector intuitively represents the type of information that we want at this time step. And then we're going to compare the query vector to each of the keys to find the one that is the most similar. And that will tell us which time step in the input is the most relevant for this time step in the decoding process. And then we will send that information to the decoder. So here maybe the second time step key is the most similar to the query, so we'll pick that one and we'll send its corresponding hidden state to the decoder. So some crude intuition for what this might do is the key might encode some notion of like, I want to know what is the subject of the sentence. And, the key might encode like, this word is the subject of the sentence. And then the query might encode, I want the subject of the sentence. And then maybe some other part might say, I want the object of the sentence, or I want a verb, or I want an adjective, right? or maybe it'll encode, I want the word that follows the word right? So the key encodes some notion of what is going on there in the sentence. The query encodes which bit you want, and then you find the key that is most similar to the query and take the corresponding time step, take its hidden state, and feed it into the decoder. So that's the high-level intuition for what we're going to be doing. I haven't made this very precise mathematically, that's coming later, but that's the high-level idea. Now, critically, we don't have to specify any of these things manually. This whole network will still be trained end-to-end, and the actual content of the keys and queries will be determined by the neural network. Just like the filters in a ConvNet, they have some kind of intuitive meaning, but they're not specified by hand. They're learned as part of the training process. Here, too, the key and query will be learned as part of the training process. So in reality, what the keys and queries mean is learned. We don't have to select it manually. And this intuition, I'm just giving it here just to help you understand why we might want to do this. Okay, so that's keys and queries. Now let's talk about how this actually can work in practice. I'm going to use the letter H to denote the hidden state for the encoder. So that's the RNN activations. I used the letter A to refer to them before. I'm going to use H now because I'm going to use A for something else. Right, the word attention starts with A, so that's going to be called A. The state of the RNN now is referred to as H. And I'll use a different letter S to denote the state of the decoder, just so that we don't confuse encoder state from decoder state. Right, they're both hidden state, they're both RNN activations, but I'm just going to use H for the encoder and S for the decoder, just to make it easier for us to separate them. And for the key, I'm going to use the letter K, and there's a separate key at each time step, and the key is some function, K of HT. So it's the same function at every time step, and it's just some function that we apply to the hidden state of the RNN. So you take the RNN encoder activation at step T and apply the function K. It could be, for example, just a linear layer followed by a nonlinearity. And again, very often in practice, the function K is just a linear transformation. So it's just like W times HT. But it could also be nonlinear if you want. The query, similarly, I'll use the letter Q to denote it, and I'll use subscript L instead of T. So I'll use T to index time steps in the encoder and L to index time steps in the decoder. So QL, for example, Q2, would be some function Q applied to the state of the decoder at that time step. And then the attention dot product, which is a kind of score that denotes how similar a key is to a query, will be given by the dot product between KT and QL. So I'm going to use E subscript T comma L to denote the dot product between the key at time step T and the query at time step L. And intuitively, we want to pull out the hidden state HT for the time step T for which ET comma L is largest, meaning the dot product is largest. So we can call this an attention score for the encoder step T going to the decoder step L. So every decoder step L will have, of course, different attention scores because it has different queries. Intuitively, what we want to do is we want to send the HT to the decoder at time step L for which ET comma L is maximized. So we're going to find the argmax with respect to T of ET comma L, and we'll send the corresponding HT to the decoder at time step L. Now, the problem here is that argmax is not a differentiable operation. So if we actually used argmax, we would not be able to train this thing. So instead, what we're going to use is a softmax, because a softmax is differentiable. So we're going to create a vector that we're going to call alpha L, which will be obtained by applying a softmax to T comma L for all values of T. So that means that alpha T comma L is the exponential of ET comma L divided by the sum over all the other T's of the exponential of ET prime comma L. So the larger the E's are, the closer this softmax becomes to a hardmax. So it's a kind of softened approximation to the max. And then if we want to send the HT that roughly corresponds to the largest ET comma L, then what we're going to send, and we refer to this as A for attention, we're going to send the sum over t of alpha t comma L times ht. So intuitively, these alphas, there'll be small numbers for all time steps t, except for the one that has the largest et comma L. So this weighted sum of HTs will be dominated by the HT corresponding to the argmax of ET comma L with respect to T. So that'll create a vector AL, which is just a linear combination of different HTs that is probably closest to the HT corresponding to the time step with the largest ET comma L. And then we'll take that AL and we'll give it to the decoder to use to help it decode the right word. Okay, so this weighted sum, weighted by alpha, approximates HT for argmax with respect to T of ET comma L. Okay, so there's a bunch of math on the slide. It's fairly simple math, but the intuition is we're trying to pull out the encoder RNN state HT for the time step T corresponding to the largest dot product between the key and the query. The reason we call this attention is because the network is trying to pay attention to the most relevant part of the input. Okay, now what does send mean? What does it mean to send AL to the decoder? Well, it could actually mean a number of different things, and these ALs can be used in different ways by the decoder. So one way to use it is to give it to the function that actually produces the output. So before, our RNN was producing the output y hat by just using SL. So y hat L is some function of SL. Now, y hat L could be a function of SL and AL. So if you're trying to figure out what word to produce at time step 2, you use the decoder state at time step 2, which is S2, and you use the encoder state corresponding to the highest attention. Ideally, it would be H2, but the soft version of that would be A. Another way that you could use this attention is you could give it to the next RNN layer if you're using a multi-layer or stacked RNN. So you could have attention at layer 1 and then give it to the as an additional input to layer 2. Another way you could use it is you could give it to the next decoder step. So here you have to look up the attention the step before and you hand it to the next step. So at the next decoder step, remember in a regular RNN we would take the hidden state of the RNN, SL-1, and we would add the input XL. Now we might add the input as well as the attention vector. So essentially in this case, the attention vector AL serves as an additional input. So you give it the new word, and you give it the attention, and the previous RNN activation, combine them together to get the next activation. So that's also a very reasonable way to do it. So all of these are reasonable choices. Okay, so let's walk through how attention would actually work in a concrete example. So we have our short sentence about the puppy from before, and each of our time steps for the encoder produces a key. And we'll start with the first time step of the decoder, and it produces a query. So we take that query and we dot product it with each of the keys. So that produces a single number for every input time step. And we call those E. So it'd be E1, E2, E3. Then we pass them through a softmax. So that just ensures that they're all positive and sum to 1. And that results in alpha 1, alpha 2, and alpha 3. And maybe alpha 3 is largest for the third time step. So then we take these alphas, and we take all the input hidden states, H1, H2, and H3, and we construct a weighted combination of the H's weighted by the alphas. So that gives us a single vector of length equal to the H's. And then we somehow use this vector to improve the decoder. One of the ways we could use it is we could include it in the function that produces y hat. Another way we could use it is we could give it to the next decoder time step. Okay? And then when we move to time step 2, at time step 2 we again produce a query. We again compute the dot product of that query with each of the keys. We again pass it through a softmax. And then we again construct this weighted combination. And then we use it in some way to produce the output, or we hand it to the next time step of the decoder. And the same thing at the third time step. Okay, so that's basically how attention works. And let's now write it out more precisely in equations. During the encoding, we have to construct these KTs, and each KT is some function K of HT. On the decoder, we produce a query QL, which is a function Q applied to SL. We construct our attention scores, ET, L, by taking KT and taking its dot product with QL for every T. You pass that through a softmax to get alpha T, L, and then you construct the attention vector AL as a weighted combination of the hidden state HT at every time step, weighted by the corresponding alphas. And then you could use this AL in various ways. You can concatenate it to the hidden state to give to the next time step of the decoder. You could use it for the readout, so you have some function that produces y hat based on ST and AL. Or you can concatenate it as input to the next RNN layer if using a stacked RNN, like that seek-to-seek example that had 3 stacked layers. So these are all reasonable choices. Now there are a number of variants on this attention recipe and a number of special cases that are worth knowing about. One very simple choice is to use K and Q to be identity functions. So in this case, KT is just HT and QL is just SL. So in this case, when you're decoding, your attention score is just the dot product between the input hidden state and the decoder hidden state. So intuitively, this is like saying, find me the time step that is closest to this decoding time step in the input. And everything else works the same way. That's a pretty reasonable choice. It's very easy to implement, but it can have somewhat limited expressivity because then you can't put something into your hidden state without having it participate in the attention. Another really simple choice, and this is a very common choice, is to use a linear multiplicative attention, where KT and QL are just linear functions of the hidden state. This is actually very reasonable because, remember, the RNN hidden state is formed by applying a nonlinear function. So it wouldn't be too hard for the RNN to just cram some information into its hidden state that can directly be used as a key or a query. So this doesn't really diminish our representational capacity very much because the RNN is already nonlinear. So it's pretty easy for the RNN to just make part of its hidden state correspond to a key or to a query. And then you can think of this weight matrix as essentially just selecting those entries. This is very convenient implementation-wise because when you compute your attention score, you have to implement KT dotted with QL, and KT dotted with QL is just KT transpose times QL. And if we substitute in the equations for KT and QL, that corresponds to HT transpose WK transpose times WQ times SL. And that means that you can combine the matrices WK and WQ into one matrix WE, which is given by WK transpose WQ. So instead of actually learning separately WK and WQ, you can just learn one matrix WE. And that can be a little bit easier to implement and a little bit more efficient. And then the rest of it works exactly the same way. You compute alpha by taking the softmax and compute the attention vector by taking the weighted combination of the H's. The last variant that I'm going to describe is actually a little more complex than the initial one. It's the same as the basic attention that I explained so far, so it has some key functions and some query function, with only one difference, which is that at the end, when you actually construct your attention vector, you don't construct a weighted combination of HTs, but instead you construct a weighted combination of HTs transformed by some learned function V, and V here stands for value. So this has kind of an appealing interpretation because now your attention during encoding, you produce key value pairs. So K of HT is the key, V of HT is the value. And then when you're decoding, you find the time step with the largest product between K and Q, and you take its value. And this can give a little bit of added flexibility. Okay, so a summary of attention. Every encoder step T produces a key KT. Every decoder step L produces a query QL. The decoder gets sent. The encoder activations HT that correspond to the largest value of the product, KT and QL. But of course, actually taking the max is non-differentiable, so you actually get a weighted combination weighted by alpha T, which is obtained by using a softmax. Why is attention good? Well, attention is actually very powerful because now all decoder steps end up being connected to all encoder steps. So the RNN itself its connection, the length of that connection is O of n between every pair of time steps. So that means the gradients need to propagate on average n steps. But the connection through attention is always O of 1. There's always a one-step connection to every encoder step. So connections go from O of t to O of 1, which means you have very short paths for the gradients, which means the gradients will be much better behaved, and you'll have much easier training. Right? The gradients are better behaved because you have this O of 1 propagation length. Or put another way, the number of Jacobians that get multiplied together along the attention route is O of 1. It's still O of t along the RNN route, but you have this other O of 1 path, and that path will train very well. This becomes very important for very long sequences, where pushing gradients through just the RNN backbone all the way between the beginning of the input sentence and the end of the output sentence can become prohibitive. That basically, even with things like LSTM cells, the vanishing gradient problems may not be avoided completely, but with attention, they don't need to be avoided completely because attention has these O of 1 connections. So this is a very powerful concept, and we're going to build on this concept a lot in the next lecture when we talk about how we could develop models that use only attention. So in practice, though, even if you just want a sequence-to-sequence model, this works much better in practice because it makes the bottleneck just much less important.